All right, it's Friday. Yay. Let's see, not too many announcements today. Homework 6 is due a week from today. At least that's the tentative due date. I'll have a better idea once we get closer to it, but so far so good. Also, I sent an email out last night giving a public lecture tonight. Don't feel obligated to attend, but if you want to, you're welcome to. It's the Greensboro Astronomy Club. Of course, it's being delivered on Zoom, so anyone can watch, and I sent the link around. And I'll be talking about black holes, the two different types of black holes, how we observe them, and that's my area of research, so I'll be talking about some of my own stuff too. If you're interested, if you have nothing better to do on a Friday night during a pandemic, there you go. Okay, questions about anything before we get going? Okay. Well, the warm-up question, let me turn the light on there. Just checking my video to make sure, yep, we're still good. We didn't get through enough stuff to actually answer this last time, but we will very shortly, so I'll come back to it. I see a handful of you have already entered answers. Maybe you did the reading, maybe you took a guess. That's all cool. But yeah, we'll cycle back to this in just a little bit. So last time we started talking about the Earth. You know, we entered lesson 6, which is on the Earth and the Moon. We started talking about the Earth. We focused on the Earth's interior. In particular, its core. Yeah, go ahead.
Are you screen sharing?
Yeah. When I came back, I forgot to screen share. Yeah, okay, 1 second. Okay, all good. Yeah, so a lot of you couldn't see the question, but again, that's okay because we haven't actually gotten through all the material to answer it. And I'll come back and put it back up in a little bit. Okay, yeah, so we were talking about the Earth's interior. We talked about the core, the outer core, the inner core. We talked about Earth's magnetic field, which is generated from the outer core. Let's continue to work our way out. So after the core, we have the mantle. Switch over the slides here. So. And the mantle can be broken into two parts as well. You have a lower mantle and you have an upper mantle, just like you have an inner core and an outer core. And the upper mantle, we call that the asthenosphere. It's the technical term. And it's rock. The mantle's primarily rock, as we talked about. We had differentiation because Earth was in a molten state for a sufficiently long period of time that the heavy stuff could sink down and form the core. The rocks float up on top of that. And then, of course, Earth solidified. But the upper mantle it's kind of still a fluid, a little bit. We'll just describe it as soft. I mean, if it were exposed and you were standing on it, it'd probably feel like rock, but it does move very slowly with time. Something like a centimeter per year. It's sloshing around in there on certain cycles that we'll take a look at. It's kind of like when we were talking about refracting telescopes made of glass. Glass we know is a solid, but over decades and the better part of a century, a lot of the old refractors have broken because the glass under its weight moves with time, flows like a fluid, very slowly moving fluid. The same is true with the upper mantle.
Dr. Reichert, does this explain the significant geological changes that happen over a planet over time? Like, say, for example, I know here the big one is like Mount Everest, which grows like an inch every year or so, if I remember correctly.
Yep, and we'll be getting there in just a second. So very good. Yep, exactly. And but let's take care of the inner mantle first, the lower mantle. And then we'll come back to how the motion of the upper mantle does just that, affect geological phenomena. So the lower mantle is solid. And again, this may be strange because, you know, the deeper you go, the warmer it gets. And so if the upper mantle is like a slow, I describe it as plasticky. It's not made of plastic, but it moves slowly like plastic would. The lower mantle is even warmer. You may expect it to be more plasticky, more fluid, but it's not. It's solid, and it's solid by pressure. Just like the inner part of the core was solid by pressure, with all that weight above it, it squeezes it and holds it into a solid form, even though the temperatures are enough to break many of the molecular bonds. Okay? So let's talk about the asthenosphere. And riding on top of that is the lithosphere, which is the technical word for the crust. I'll just write that here. And we'll get to the lithosphere in a second, but the asthenosphere, we're going to have convective cycles, just like, well, any fluid layer, like the outer mantle, the outer core is fluid, so you're going to have convective cycles. We're going to see this in some of the atmospheric layers as well. If you have a fluid, even if it's slowly moving, you'll get these convective cycles. And what it is, it's hotter below, and so that material being warm will expand. When it expands, it's low density, and we know it's just differentiation. Sorry, bang the microphone there. Low density stuff floats to the top. We saw that with the golf ball and wiffle golf ball example last time. So that material, the warm, expanded, slightly lower density material will rise up. Then it releases its heat into the lithosphere, the crust. Then it's cool, so it contracts and it's higher density and it sinks. And so this is going on very slowly, as Claire said, like an inch every year. It's kind of a great number, inch per year. It's the rate at which convection occurs, the rate at which Everest rises, the rate at which the continents drift. All those things are connected, of course. It's the rate at which your fingernails grow. It's the rate at which the moon is moving away from the Earth. It's kind of a catch-all number that hits many different phenomena. But anyway, here the convective cycle is drawn in, kind of organizes itself into regions where you have hot material coming up, and then it loses its heat and it's pushed sideways because new material is coming up underneath it. And then it finds places where it sinks. And it just kind of organizes itself into these cells. And then you have the lithosphere, the plates, the crust. And that's, of course, solid. It's not solid by pressure. There's nothing above it squeezing down on it. It's just cold enough. It's cool enough it can be solid, just solid by temperature, normal solid. But it's riding on top of these convective cells. And so the plates move, and that's, of course, plate tectonics, which you've learned about since grade school. And here's the Pangea sequence. We all know that the continents are spreading apart because they're plates. They're riding on the mantle down below. And if you go back 200 million years, all the continents were kind of connected. It's kind of obvious if you look at a map. South America seems to fit in perfectly with Africa, and you can see how it would piece together. Lots of people speculated this before we understood these motions. But keep in mind, this is only 200 million years. This isn't the beginning of the process. Earth's been around for 4.5 billion. We can trace this far back pretty easily. I think they have some ideas about where this was before that, but it's hard to think of all the many times it expanded and ran into each other and expanded and ran into each other. And there's no way we can track that all the way back through time. But the most recent cycle, we kind of get the gist just by watching how the plates are moving. If we run forward from 200 million years ago, here's 130 million, here's 65 million, which is, of course, when the dinosaurs were wiped out. And it's, the arguments are, I'm not a geologist or anything, but the arguments are more than just the shapes match. You have similar geological structures on both sides. You have similar biology and fossils. Like there may be some kind of animal, maybe a dinosaur that lived in this region right here. And so in the modern day, we see their fossils here and here, right? So there are all sorts of ways you can make these arguments. And here we are, of course, in the present day, and it's continuing to move. The Atlantic is increasing and forcing the continents to shrink the Pacific. And eventually, a long, long time in the future, our west coast will run into the Eurasian east coast.
I have a quick question.
Yeah, go ahead.
Do you know if there's a model that like shows what it'll look like in the future, like when they run into each other again?
There probably is. I don't recall seeing that off the top of my head, and it's extrapolation, which is always a little dangerous. If you assume all the plates keep moving on their current trajectories and make some assumptions about what happens as they run into each other as they move, you probably can extrapolate this forward. I'm not sure if you can go all the way to the closure of the Pacific, but I wouldn't be surprised. It's probably worth Google searching. Okay, so why is the Atlantic getting bigger? Well, we have this big ridge. It's not just one spot where the material is coming up. It's a long linear segment running the kind of the length of the Atlantic. Here you can see it in an elevation plot where they've taken out the water. Normally this is all underwater, or most of it anyway. But you can see where this ridge is, and it's just new stuff's coming up there and pushing apart. Kind of off the top here, we have Iceland. You have maybe just a little hint of it here. It's off the top of this image. And Iceland is just some of this new material that has come up and it's poked above the surface of the water. Iceland periodically gets new islands. There are all sorts of little islands around it, and some of them are relatively recent, like decades recent, which is amazing. Oh, and here's a little aside that ties back to the magnetic field flipping that we talked about. They've gone down underwater and brought up rock samples. Now, as the new rock comes up, it comes up in a molten form, and there's little molecules in there that have iron in it that want to align themselves with Earth's magnetic field, which it can do while it's in a molten form, and then it solidifies and it gets locked in place. And so by bringing up rock samples, they sampled over a pretty large area. That's a pretty big part of the seafloor. They brought it up and they see that these iron, I'm not sure exactly what kind of molecule, but it has iron in it. They keep reversing direction periodically. So this is the more recent stuff, and it's older stuff the farther out you go. And it's evidence that the Earth's magnetic field is flipping every million years or so. And it's not super periodic. It's not super predictable. You can see the ons and the offs. It's a little bit messy, but it's basically every million years you get a reversal. It's the Dynamo Effect. Again, we talked about it in the sun. It happens every 11 years very predictably. Well, so these plates, the crust, they're floating around on the asthenosphere, and they're going to run into each other, and they'll run into each other in a variety of ways. Sometimes they'll run into each other and push each other up. I'm not sure the technical term. Maybe it's uprising. You can have two plates run into each other and one pushes over top of another. This is called subduction. And the other motion is if they're going in opposite directions, and this is called shear. And these are not exclusive. You can have either of these with the shear. They're maybe one is subducting the other, but they're also sliding this way. In fact, they don't have to be opposite directions. They can be the same direction, just different speeds, and you'll have a shear as well. And all these have certain geological consequences. A good example of the uprising is India plowing into the Eurasian plate, causing the Himalayan mountains. If we go back to our Pangea sequence, you can see India, it's actually on its own plate, and it was separate from Asia, and only recently has run into it, and it's continuing to move into it and it into India, and so it's pushing up like this. And so that mountain range, tallest on Earth, is still rising as the convective cycles underneath continue to push that plate in that direction. They've measured.
Eckhart.
Yeah, go ahead.
Okay, so I don't know if you explained this already, but what happens every million or so years when the Earth changes its magnetic field? Like, what changes?
So the North Pole becomes the South and the South becomes the North, and just a basic flip. Though during the transition period, it's a little messy. I don't think we have much direct evidence, but we speculate that we're not left defenseless. We don't have no magnetic field. It's just kind of all over the place with lots of North and South poles, little magnetic bubbles instead of a global shield.
So are you saying that it's a sudden change, or are you saying it's a gradual change over time?
Depends on your definition of sudden and gradual. Over geological timescales, a century or two is pretty sudden. Over human life scales, we would consider it a gradual transition. But yeah, in the grand scheme of things, it's pretty sudden. And with the sun, where we see the same thing going on, just kind of bulked up on steroids in a much faster pace, yeah, it's pretty rapid. You have 11 years of it oriented one way, and then snap over the course of a couple months, it's rebuilds itself the other way.
And you said this cycle happens about every million years?
Yeah, for Earth, every million years, yeah. On the sun...
Is there a reason for it? Like what causes it?
It is, so with the magnetic field flipping, it is what's going on in the outer core. We have all these little, go back to my Microsoft Paint edition here, all these little eddies that are kind of spinning around in there. It's material that's been churned up by Earth's rotation. And I'm doing this in a very hand-wavy way. There are people far more expert at this than me. And it's by no means a fully understood problem. It's very complicated because it's not just hydrodynamics, which is the term meaning the physics, the motion of fluids, but it's magnetohydrodynamics because you have magnetic fields being generated by the motions, and those magnetic fields can also impact the motions. The very complicated, messy thing. And they're always changing and combining and breaking apart. And that's why the magnetic pole wanders around. But every so often, the whole thing kind of falls apart and it reorganizes itself with the eddies kind of going the other way, and causing the magnetic fields to be flipped. Not the best answer, but that's at least the limit of my understanding of it. Again, we're into geology and areas that are a little bit outside of my training. Okay, so we have the uprisings. A good example of the subduction, which was the second example here, is our West Coast. There's a Pacific plate and the North American plate. The Pacific plate is ramming itself under, or actually, you know, the Atlantic is spreading, pushing our continental plate, the North American plate, over the Pacific plate. But one sliding over, one sliding under. So it's a subduction area. And you have this kind of really wet Pacific plate being pushed under our plate. It's carrying a lot of moisture down. There's a lot of friction. And once that gets down into the asthenosphere, that friction, that moisture, it can melt the rock. The rock's moving slowly, but it can melt it. So you have little pockets of lava, and they'll find cracks and work their way up to the surface, giving you volcanoes. So whenever you see subduction zones, if you look inland, not right at the boundary, but inland a ways, you'll find mountain chains and volcanoes and things like that. And we have them here in the US. Mount St. Helens is the most recent example up in Washington State. It blew its lid back in 1980, before you were all born, but I was alive. I was 6. And I grew up in Pennsylvania. And I remember like 3 days after this happened, our skies darkened. That's how powerful this is. You know, it blew up, darkening the skies there, but then the Gulf Stream carried it completely across the country. And then the last example is shear, where they're moving either opposite each other or in the same direction at different speeds. And that's what we have also with the North American plate and the Pacific plate. Here you can actually see the boundary where one is subducting under the other, at least down below, that's what's going on. But they have this kind of shear as well, and there's a lot of pressure. So normally the rocks are locked up and the pressure builds and builds and builds, and then it jumps forward. And of course that will shake the earth and create earthquakes, which is where we started this whole thing. You know, we've been probing the interior with earthquakes and learned how the interior works and how the earthquakes are generated. Gone full circle.
Can you explain again why the subduction causes the eruptions?
Yes, so as one plate is pushed under another, particularly if one plate is covered in water, that rock will be wet. And as it's sliding under, there's a lot of friction, which generates heat. And particularly if you have wet rock that you're heating up, that wetness, that moisture is going to transition from liquid to gas and increase the pressure. And you'll end up with these hot regions somewhat inland. You got to wait for the one plate to push all the way down to the asthenosphere where the rock is softer. But between the friction and the moisture, you can create regions hot enough to produce lava. And then they have to work their way up through cracks and crevices they find in the lithosphere, in the crust, and they can break through. And normally it's not a constantly ongoing thing, but you know, because you have mountains and stuff, but as the pressure builds and builds and builds, eventually you can break through suddenly. Yellowstone's another great example. It's a little bit more inland, but it's not a volcano, but it's a whole region where the molten interior is trying to work its way up. And so we get earthquakes on this particular fault line. Here's San Francisco, 1906. There was a very big earthquake then. And it actually didn't destroy the buildings, but it caused a fire that then destroyed the buildings. And we've, of course, rebuilt San Francisco. And we now have very stringent building codes, particularly near the fault lines. So our buildings should be able to withstand pretty major earthquakes. Here's an interesting one. This is kind of a fun one. Chile, my telescopes in Chile are pretty close to the same significant kind of fault line. And this was back in 2005. There was a major earthquakes in Chile and Haiti that year. And here these are images that were going on the prompt telescopes. They're pretty new at that point. Someone was imaging just a field of stars. And this is the image before the quake. This is the image during the quake. It was actually shaking the telescopes, even though the epicenter was like hundreds of miles away. And then we lost the internet for 2 weeks. It broke, and it was that bad of an earthquake. But they didn't suffer a lot of damage in terms of their buildings because they also build by the same stringent codes. But Haiti, the earthquake was far less powerful, but it created a lot bigger problem and destroyed lots of buildings because just the code, the engineering code is more lax there. Now, that's what happens if it's on land. If it's underwater, you release a tremendous amount of energy. You can't really expand this. It's just an animated GIF. This is the Thailand earthquake from a number of years ago. I think they made a movie about it with Ewan McGregor, he's my man crush, I guess. But I actually haven't seen that movie though. Anyway, so yeah, it was set off a tsunami. You deposit a lot of energy under the water and you send these big waves across the ocean. And often they're not really big waves until they get into the shallows. It may just be a lot of energy, but a simple wave. And once it gets into shallow, then it comes up and can be very dangerous. But here you can see it's spreading across the entire Indian Ocean. These things can spread across the entire Pacific. It's pretty powerful stuff. And here you see a distribution of the plates, and the red spots are areas of geological activity, either earthquakes or volcanoes or those sorts of things. And you see they line up pretty well with the plates. Usually they're on one side or the other. Those would be subductions. And again, the volcanoes would be a little bit inland. You know, you can see the Pacific Rim, all these islands out here, clearly volcanic. The Caribbean, not active anymore, at least to my knowledge, but they were probably produced through volcanism, and there's the Mid-Atlantic Ridge and so forth and so on.
So do the earthquakes happen on the side that the plate is going over or under the fault line?
So the earthquakes would be on both sides. So those volcanoes, there are two types of volcanoes you can have. The subduction volcanoes, and then you can also have what are called shield volcanoes, which we'll learn about. The Hawaiian Islands are a good example of that. You can see over here, that's just a thin point in the plate. And so stuff's poking up through it. And as the plate moves, it pokes up and makes another island. And then it moves, pokes up and makes another island. That's separate. But in terms of earthquakes, it'll shake both sides. But the volcanoes, the subduction volcanoes, would just be on the plate that's running over top of the other plate, somewhat inland. At least that's my understanding. Again, I'm not a geologist. This is part of the course where I'm most out of my element. But let's talk about the atmosphere next. Unless there are any more questions about we've done the interior, we've done the surface, and you know, some of that geology, I'm not just going through it to go through it. We're going to see what happens on the surface of Venus, for example, and compare and contrast with plate tectonics here on Earth. There are other worlds. Ganymede also has its version, a moon has, with just ice as continents, has its version of plate tectonics. It's just different. And so we start with this, and then we can compare and contrast. But if there are no questions, we'll move on to the atmosphere. And this will be more notes than slides. Oh, actually, let's take a look at our warm-up question, though, before we move on to the atmosphere. I'll put it back up here and give you all a chance to answer if you haven't already. So select all that apply. Which of these layers are pressurized solids? Inner core, outer core, lower mantle, upper mantle, and the crust.
Do you mind showing that other page of notes for a second?
Yeah, not a problem. Put it up for a second there.
Dr. Rucker, I have a quick question. Just to clarify, like shear movement causes earthquakes and subduction causes volcanoes. Is that correct?
Yep. Causes subduction volcanoes. The
Okay.
shield volcanoes are separate, and we'll get to those in a bit. Now, I acknowledge that like 27 of you put in guesses before we covered the material, so if it's not perfect, that's fine. But maybe another 5 or 10 seconds, and we'll see how you answered. Yep, and so the answer is 1 and 3. A lot of you probably put 1 because that's all we had covered in the previous class, but now we also introduced the lower mantle as a pressurized solid, but not the lithosphere. It's solid, but not due to pressure. It's solid due to temperature. Okay, good. Let's move on to the atmosphere. I'll make the notes big here. And to really understand the atmosphere, we have to do an aside first and talk about what are the most abundant elements out there in the universe. And this is useful information that we'll keep folding back into the remaining lessons. So, you know, for the universe as a whole, that's my symbol for universe, the capital U. And let's have most abundant down to least abundant. So under most abundant, we have hydrogen and helium. Hydrogen's about 75% of the stuff out there. Helium's about 25% of the stuff out there. So the universe is primarily just these two things. Originally, it was only hydrogen, but the early universe, shortly after the Big Bang, between minutes 7 and 20, if we want to be precise, the universe everywhere was hot and dense like the inside of a star. And so fusion was going on everywhere in the universe, like it does in the inside of our sun, converting some of that hydrogen to helium. But it was just a short period where the temperature and pressure was right. So that's all that got converted. Stuff we talk about in Astro 102. But anyway, after minute 20, that kind of set the composition of the universe. And then there's a division at much lower abundance, right? Because that's almost 100%. I put little squiggles there because there is other stuff. We're made of other stuff. The next three big elements are carbon, nitrogen, and oxygen. These are made in the bellies of stars, and some of the stars explode and scatter this stuff throughout the universe. So ever since the Big Bang, this has been going on. And to make enough, like we're carbon-based, and clearly nitrogen and oxygen is a big part of Earth's atmosphere, our existence. To make enough of this stuff to make the Earth, make us, you have to go through about 50 stellar explosions. And the material gets recycled and built into new stars. So you have gone through about 50 supernova explosions, which is a nifty little factoid. And then much less than that, you have trace elements of everything else. So there's kind of three categories: lots, a little bit, and then hardly any. Let's not worry about the trace elements right now. Now, of these elements, only helium is happy by itself. It's a noble gas. It's inert. Its outer shell of electrons is full, so it's not going to interact with anything chemically. But all these others, they have open holes in the outer shell. So hydrogen, well, to fill these holes, hydrogen loves to bond. Hydrogen has one electron, and it's the most abundant thing in the universe. So the most likely combination is the open spots get filled with hydrogen. So hydrogen merges with itself to make molecular hydrogen. H2, we call that molecular hydrogen. This would just be atomic hydrogen. Carbon, you have 4 of these places you can bond, so you get CH4, and that is methane. Nitrogen has 3, so you get NH3, and that's ammonia. And oxygen has 2, so you get OH2, which we normally write as H2O, which is, of course, water. Methane, ammonia, water. Methane, ammonia, water. We're going to hear about these for the rest of the course. They play a big role in what's going on the surfaces and interiors of the planets. So back to our early atmosphere. The early atmosphere is made of these 5 things because Earth forms by stuff gravitationally attracting, and the more mass we get, the easier it is to pull stuff in. We get bigger and bigger, and this is the stuff that we're pulling in from space in these proportions, mostly this stuff, but also this stuff. So our first atmosphere is molecular hydrogen, helium, methane, ammonia, water. I'll just MAW for short. But the problem with the first atmosphere is it's just too hot here on Earth. I said the formation of a planet's a very hot process. As stuff moves towards the Earth, it picks up speed and eventually runs into the forming material, transferring its energy of motion into heat. And of course, we keep having bombardments, not just of atoms and molecules coming in, but little planetoids that have been forming. They hit the Earth. There's the radioactive elements. All the stuff we talked about keeps Earth hot and molten for about 500 million years. And it's hot enough that these gases, the ones that are floating around on the top, since they're so hot, the molecules are moving really fast and they just escape. They're moving faster than the escape speed. And so they float back off into space. So the first atmosphere is lost. All this stuff goes into space. And we really won't have an atmosphere until it cools down to the point that we can retain some of this. So the second atmosphere, I'll give you a second there. I'm going to move this. The second atmosphere comes from our, the volcanoes. As Earth begins to solidify, initially we had lots of volcanoes. It was much more volcanically active. And so our second atmosphere comes from volcanic outgassing. And it's pretty much the same stuff. Some of it modified a little bit. A lot of these gases and things, when they're trapped under the earth, they go through chemical reactions. So let's see what comes out. Basically the following things. You have water, H2O. You have methane, CH4. You have a variety of nitrogen compounds, including ammonia. Then you have CO2, carbon dioxide, and SO2, sulfur dioxide. And this stuff is heavier, I should just point out. Right? Hydrogen's lightweight. This has one heavy thing, this has one heavy thing. These usually have one heavy thing, nitrogen, but these each have three. So they're heavier elements, that molecules that have come together under the surface. And let's go through the progression of what happens to each of these. Let's start with the nitrogen compounds. So UV radiation from the sun breaks off the N from the nitrogen compounds. Ultraviolet light, we don't have an ozone layer protecting us yet, so the ultraviolet high energy light gets through and it can break chemical bonds. Breaks off the nitrogen, and then you have this nitrogen floating around, and it will bond with some of the other nitrogen floating around, giving you N2, molecular nitrogen or nitrogen gas. And that's what our atmosphere primarily is right now. We don't use it as part of our breathing cycle, but it's the bulk of what's going in and out of our lungs. And it breaks off the nitrogen. The rest of it, in the case of ammonia anyway, the rest of it's like hydrogen and stuff. And that just, it's still warm enough that the lightweight stuff will float up into space. So the hydrogen that breaks off of ammonia goes off into space, but the nitrogen will bond with another nitrogen, get heavy and sink and stay around. So that's nitrogen compounds. Let's take a look at the water here. The water, the H2O, it's cooler now, so it can liquefy. It liquefies and it falls down from the atmosphere and forms lakes and oceans and rivers and things like that, but primarily the oceans. And that's supplemented by, where is it? By comets. Again, the early solar system is a very busy place. There are all sorts of little planets that didn't quite make it, which we now call asteroids and comets and things like that, floating around, running into the planets, much more so than currently. So a lot of water was brought to Earth through cometary bombardment, or so it's thought. So the hydrogen liquefies plus comets gives us our oceans. And once we have the oceans, then our carbon dioxide and the sulfur dioxide. Now, some of it stays in the air, but a lot of it dissolves in the oceans, producing essentially the rocks. You know, rocks are formed geologically. We don't have rock molecules out there in space. We have the components, and then they go through these geological processes to make rocks. And again, I'm no geologist, but my understanding, most rocks have oxygen in their chemical signature. It's coming from the carbon dioxide and the sulfur. It gets into the water. The water is a fluid medium where they can move around, interact with other things, and start to build up the rock layers. And then the last big change is induced by life. So life forms on Earth 3.5 billion years ago in the oceans. And they start converting CO2 into O2 and O3, like plants do today. We convert oxygen into CO2. Plants convert CO2 into oxygen and also O3, which is ozone. And the ozone then works its way up into the atmosphere, producing Sorry about these notes. They're kind of all over the place. The ozone layer. And that ozone layer, as we'll learn, protects us, it protects the surface from high energy radiation. The ultraviolet and heavier energy, like higher energy, like X-rays, gamma rays coming from the sun, but primarily ultraviolet, used to just come straight down to the surface, and that makes it challenging for life. But once that ozone layer gets there, it's a protective blanket, and life can move out onto the land at that point. And so life moves out on land, and life develops that, well, it moves out onto land and continues this process of converting carbon dioxide into oxygen and ozone. And now there's a balance, you know, how much oxygen we have versus carbon dioxide. It's a balance between how quickly we convert stuff versus the plants. This is kind of the history of our atmosphere. And I'll give you just a second if you need to capture any more notes or screen capture that. And then I'll go to a blank page and sketch out the current atmosphere, what we have today. Okay, going once, twice. Okay, done. So today, we have N2, that's 78%, and that's measured by volume. These things can be measured by volume or by mass. This is by volume. We have O2, which is 21% by volume. There's argon, which is a noble gas. So, you know, whatever argon came in, it's heavier. Like helium, a lot of it just escapes. But if you go below helium on the periodic table, you have argon, it's heavier, so it sticks around. That's 0.9%. Doesn't do anything, it's inert. You breathe it in and out with no consequence. Then you have CO2. It's about 0.03%. So a very small fraction of our atmosphere is now CO2. The plant life has converted most of it into oxygen. There's only some still here because we convert some back, and this is before it's taken in by the plants. If you add all this up, it's 99.93%. So then you have trace amounts of everything else. But there's one that I left out on purpose, and that's the water vapor. We have water in all three stages, solid, liquid, and gas. There's water in the atmosphere. And I left it out because it varies tremendously from place to place. It could be anywhere from 0.1% to about 3%, like 0.1% over the deserts and 3% over the rainforests. Of course,
by water vapor, do you mean like humidity or the water that's in the air, or the clouds, stuff like that?
Yeah, both. Yep, humidity, clouds, yep. Just water molecules suspended in the atmosphere. And of course, that adds up to more than 100, so you'd have to rescale depending upon what number, but you get the idea. Now, this water vapor, and this is something we'll talk more and more about because it happens on the other planets. And, you know, the greenhouse effect is like a political football. I mean, scientifically, it's well understood and not debated, but it's a political football here. But there's no way we can understand the other planets without understanding the greenhouse effect. And so and we'll come back and talk about it more, but the primary greenhouse gas is water vapor. And, you know, if it wasn't for water vapor, here in North Carolina would be under 3 miles of ice right now. And also, of course, carbon dioxide is a greenhouse gas. And they do both occur in natural levels. But due to, as we'll talk about, due to industry, we're producing more CO2. It's the less potent of the two. Fortunately, we're not producing more water vapor. If we did, the atmosphere saturates and it just falls back out as rain. If we could put more water vapor in the atmosphere, we'd really be screwed. Just increasing the carbon dioxide and the methane and NO2 by small amounts does have consequences for the climate that we'll talk about very briefly. But anyway, know that this is water vapor is a greenhouse gas, but it's important, good greenhouse gas in this case. Okay, come back to that, but let's talk about the atmospheric. Yeah, go ahead.
So you said that water vapor could make up 0.1 to 3% of the atmosphere?
Yeah,
How does that work with you saying that those other elements are 99.9?
that's right. So these elements are not, these percentages are out of everything except for the water vapor. And so you have another 0.07% of other stuff, and then you'd have to add this on top and then renormalize it.
Okay.
So if it's 3%, basically divide all these numbers by 1.03, and to rescale it over those parts of the Earth, everything's a little bit smaller because you have this extra component.
So basically, it's like a percentage of a percentage.
Yeah, that's right. So these are percentages of the atmosphere out of everything except for the water vapor. And then if you want to add the water vapor in on this scale, it would be kind of in this range. Of course, that brings you over 100%. So you have to divide by 1.0 whatever the total is to renormalize it. So it will vary. These numbers vary from place to place just because you're squeezing in a little bit of this. It's kind of a technical math thing that doesn't matter that much. You get the basic idea. It's mostly this and this, small amount of that, but also this important greenhouse gas, which varies from place to place. That's the main takeaway. Okay, let's see if we can run through some of the atmospheric layers. We won't get through all of them, but we can get through some of them here. And then we can move on to temperature discussions next time. So the atmosphere, that's the next layer up. And we have 4 layers: the troposphere, the stratosphere, the mesosphere, and the ionosphere. And the bottommost layer, the one we live in, is the troposphere. It goes up about 12 miles. That's the top of the troposphere. What we're plotting here, this blue curve, is the temperature. So it's warmer down below, cooler up above. It flips around, the temperature inverts itself in the stratosphere. That's because that's where the ozone is, and it's absorbing that high energy solar radiation, heating those layers. But down here, the troposphere is defined until you get up to this point of temperature reversal. And this is a convective layer. Whenever it's warmer, whenever you have a fluid, either liquid or gas, and it's warmer below, you'll have convection. Because being warmer below, that gas will expand, become lower density, and rise. Then it gives up its heat at the top, and it's cooler, it contracts, and sinks. And so we'll have convective layers in the troposphere, just like we do in the asthenosphere and the outer core. And if Earth were stationary, it would organize itself into 2 convective cells, where the hot gas on the equator would rise and be pushed along to the pole, and then it would sink because it's cold up there. And you'd have 1 giant cell in the northern hemisphere and 1 giant cell in the southern hemisphere. And for slowly rotating planets like Venus, that's what you have, 2 convective cells. But Earth is rapidly rotating, and so the Coriolis effect comes into play. You may remember this figure from lesson 2. If you fire a missile from the North Pole down here, it appears to be deflected to the west, because in reality, Earth is rotating underneath it to the east. In other words, the atmosphere, this is a ballistic missile, but the same idea is with the atmosphere. Because of this convective cell, you have atmosphere moving, and it's detached from the Earth, rotating underneath it. And so the combination of these Coriolis forces and the convective motion breaks you apart into multiple cells. And the faster the planet like Jupiter rotates in half a day, it has many, many more convective cells. On Earth, we have 6. We have a polar cell, a temperate cell, and a tropical cell in both hemispheres. And if you look at the pattern over the US, and we'll be able to finish the troposphere today, this pattern should look familiar. See this kind of wiggle shape? You've seen it on weather maps before. That's the jet stream. And it's just the convective cell combined with the Coriolis force kind of pulling it around the Earth as it goes. And so that determines a lot of our weather here and, of course, other places, depending on what the cells look like there. And the last thing I'll say about the troposphere is that because of the convection and the Coriolis forces, it's turbulent. And that's why planes that are going long distances fly at the elevation that they do. They try to get 12 kilometers up, or at least close to that. They fly in the upper troposphere or even the lower stratosphere. And usually the upper troposphere, you get above most of the turbulence. So it's smoother. Otherwise, it can be very bumpy. If you've ever flown in a small plane that doesn't go up above most of that, it can be a bumpy ride. Anyway, that's why planes fly up there. Okay, that's it for today. We'll finish up the atmospheric layers next time and get into temperature measurements, which are not done in the book, but we'll use them a lot in the homework. So it's something extra. You'll definitely want to catch that. Okay, see you later.
Thank you. Thank you.
Thank you.
Thank you.
Thank you, Doctor.
My pleasure.
Thank you.
Can you explain the connective cells again? Convective cells.
Convective cells, yeah. So the way it works, whether you're in the outer core or the upper mantle, very slowly, of course, in the upper mantle, or in an atmospheric layer, if it's a material that can move, like a liquid or a gas, so this doesn't apply to pure solids, they don't move, and it's warmer below, those are the two criteria you need. If it's warmer below, whatever it is will expand. Being fluid or gas, it expands. When it expands, it's lower density. And we learned that lower density things float on top of higher density things. So the warm gas will rise and the cool gas will sink. Were you here for the golf ball example last time?
Yes.
Okay, so that's also an example of that. The pink golf balls are denser, and the white wiffle golf balls are lower density. And as I shook it up, all the low density ones rose up and the higher density ones sunk down. And so warm gas will rise, which is, you may not have known the reason, but that's the reason. And once it gets up to the higher layers where, it's cooler, it can dump its heat into the next layer up. Then that gas, losing its heat, it's now cold, contracts, becomes higher density, and sinks. And so you organize yourself into these cells that go up and down and up and down. And you can see that here. You have, here it's going up, and there it's going down. Here it's going up, and there it's going down. It's just being dragged around the Earth because of the Earth's rotation at the same time.
Thank you.
Professor, I just wanted to know that when is the optional assignment due?
With the final. In fact, don't turn it in beforehand because I'll lose track of it. Turn it in the day the finals due. Just email it to me.
All right, thank you.
Anything else?